Welcome to Now You Know. Today we're diving into significant figures, the secret to nailing precision in math and science. Whether it's chemistry or physics, this skill will level up your calculations. Let's get started. So, significant figures is really important when you come into lab. When you're dealing with things and you're getting a bunch of different measurements that come out to different decimal places and different levels of precision and uncertainty. So what's the purpose? The purpose is to help preserve the degree of precision of measurements. So it helps us round measurements or calculations to a precise number. There are some rules for significant figures. The first rule is all non-zero digits are significant. The second rule is any zero between non-zeros is significant. The third one is leading zeros are never significant. The fourth one is trailing zeros are significant when a decimal is present. So let's practice this. So how many significant figures are present in each number? So we have 726. There are no decimals. There are only non-zero numbers. So when you have this situation, you just count how many there is. 1, 2, 3. So there are 3 significant figures. How about 706? There is 2 non-zero numbers, and the only zero is sandwiched in between 2 non-zero numbers, which is right here and here. And since it's between 2 non-zero numbers, it is significant. So that would make the significant digits be 3. How about here? 7,025,000. We have 1 non-zero number, 2 non-zero number, 3 non-zero numbers, and we have 4 zeros. However, these 4 zeros are sandwiched between non-zero numbers, so they are significant digits. So in this case, we just count 1, 2, 3, 4, 5, 6, 7. 7 significant figures. Okay, how about here? We have 1 and 2 non-zero numbers. And we also have 2 zeros that are leading. And as we know from the rules, leading zeros are not significant. So in this case, we just count our 2 non-zero numbers being 1, 2, and that leads us to 2 significant figures. Let's come over here. As you can see here, there are 2 non-zero numbers, and there are 5 zeros in front. Now these are leading zeros. Even though there is a decimal, these are all leading, and leading zeros are never significant figures. So in this case, we only have 2. That's about as tricky as these get. In this case, we have 1, 2, 3 non-zero numbers. We also have 2 zeros. However, they are trailing, and there is no decimal place. So that means our significant digits are these 3 non-zeros only. So there's 3 significant figures. Here we have 1, 2, 3 non-zero numbers. We also have 2 zeros and a decimal place. Now this decimal place means all trailing zeros are now significant. So in this case, we have 5 significant figures. Let's move on to the next one. You have 1 non-zero number and 2 non-zero numbers. You also have 2 zeros, and they're sandwiched. So this leads us to counting all numbers as significant, and there being 4 significant figures. Next, we have 3 non-zero numbers. We also have 3 zeros. However, we have this decimal, and this decimal means all trailing zeros are in fact significant. So in this case, we're going to have a total of 6 significant figures. Let's move on. Next, we're going to cover rules of calculations. And of course, feel free to pause this video at any time and take notes or analyze. So The first rule of calculation is when adding or subtracting numbers, the result is limited to the fewest decimal places. So let's see an example. So as you can see in this example, we have 10.10 centimeters plus 1.332 centimeters plus 6.4 centimeters. If you were to add these up, you would get 17.832 centimeters. Okay, but we need significant figures because we have all these different measurements to different degrees of uncertainty. So in this case, since adding and subtracting, we go to the fewest decimal places, which would be right here. We get 6.4 has one decimal place. One decimal place. So we need to record our answer to one decimal place to match our significant figures. And so we do so as such. So what you would do is you would round this 3. You would round to the 8, which would be dependent on the 3. So if it's 5 and up, you round that 8 to a 9. If it's 4 or lower, you round that 8 to an 8. It remains an 8. So let's go ahead and keep our units. And let's box our answer. So let's just go in and analyze this. So one decimal place for our 6.4. So our answer is going to also have one decimal place. Okay. Our second rule of calculation is when multiplying or dividing numbers, the result is limited to the fewest number of significant figures. So this is where those significant figure rules come into play. So let's try it for this calculation. 2.07 kilograms times 15.50. If you were to do this calculation, you'll get 32.1 kilograms. Sorry, this is supposed to be meters per second. Kilograms meter per second. So now, after you calculate it, let's see about significant figures. As we see, this 2.06 has 3 significant figures, and this is less than the 4 sigfigs from here. So we would go with the 3. So our answer does in fact have 3 sigfigs. So we rounded it to the proper place. Let's try another one. We have 4.21 centimeters divided by 2.3 seconds. Our numerator has 3 sigfigs. Our denominator has 2 sigfigs. So the answer would be 1.8304 centimeters per second. However, we need to convert this to sigfigs. And as we know, we go to the fewest number of sigfigs. And in this case, it's going to be our 2 sigfigs from the denominator. So our answer is going to be 1.8 centimeters per second. Let's go ahead and box that. And let's just analyze, make sure we got 2 sigfigs. So let's move on to the next part. The next thing we're going to go into is logarithms and significant figures. So the first part of this is the number of digits after the decimal point of a logarithm should equal to the number of significant figures of x. So let's demonstrate this. Let's show this. So you have this logarithm, the log of 3.5 times 10 to the 5th power. And this equals if you were to put this in a calculator, you'd get about 5.544, and it'd go on to a great big calculating number. So let's look at this. In this logarithm, we have 2 significant figures, right? So these 2 significant figures means that after the decimal of this answer, you need two significant figures. So this is how that's going to work. You're going to take your 5.544 and you're going to force it to have two decimal places. So it would be 5.54. So this is where your two decimal places come into play. And this puts it at proper significant figures. Next, the second part of this is for an inverse log of the number of sig figs in answer is equal to the number of digits after the decimal point. So let's work backwards on this one. So to break this down, let's look at this decimal point is right here. And after that, you have 3 sig figs. Okay, so if you were to punch this into a calculator, you get this big calculator answer. And you're going to convert that to sig figs. And this is how you're going to do it. Since you have 3 sig figs here, it's real simple. You're going to convert this down to 3 sig figs. So you're going to make sure here we have 3 sig figs. So that's how you do sig figs with logarithms and anti-logarithms or inverse logs. Okay, so go ahead and try this problem. What is the answer to the following question, and record your answer to proper amount of sig figs. So the question is 12.34 grams plus parenthesis 2.5 milliliters times 1.00 grams per milliliter equals what? Leave your answer in the comments. Also, don't forget to like, subscribe, and hit the bell for more Now You Know lessons. Also, always check out the extra resources in the comments, including extra practice and the answer key to go along with it. That being said, thank you for watching and stay tuned for more. Have a good day.